subject in its various features. And the title of the talk is Synthetic Theory of Ricci Curvature. So it's important that we recall what the Ricci curvature is, but also what it means synthetic. So there is no precise definition of what synthetic is, but it is common to do opposition between synthetic and analytic. And to explain these different points of view, I will consider a few examples. But roughly speaking, analytic is when things are expressed in terms of computations, while synthetic are in terms of properties. So our first example is about the well-known notion of convexity. So we all know that there are two main definitions of convexity. The first one is to say that something is convex if it satisfies like phi of 1 minus tx plus ty is bounded above by 1 minus t phi of x plus t phi of y. Okay. For any x and any y and any t which is between 0 and 1. And this is a property of the graph saying that it satisfies the I saw different colors.
So here are some more.
Okay, very good. Thank you. So it will be this property of the graph. Okay. And of course, there is also another way to define the convexity, which is the second derivative is non-negative. So the first one is the synthetic notion, and the second one is the analytic notion. Okay. So what can we say? The second is analytic, we understand very well. We are making a computation from the function phi, and we compute the second derivative. The second definition is more precise, because when we have the second derivative, it also has some properties. So from this, we can say, for instance, easily whether something is uniformly convex, strictly convex, things like this, depending on your definition of strict, but it's easy to see how to do it. This definition is effective, one would say. You can check it in practice. I mean, if I give you a function with a formula, usually if you try to prove this directly, you become crazy. Well, this is okay. When we have convexity to prove, we always do this. Take second derivative, look at the sign. We learn to do this in calculus course. So the analytic definition somehow is more systematic. And on the other hand, this is very useful because some functions satisfy this definition even if they are not twice differentiable. For instance, the absolute value obviously is convex but has no second derivative. So the synthetic definition is more general. The next remark is that the analytic definition is obviously local, while the synthetic definition is non-local. Okay. It is actually an important property of convexity that there is some propagation. If you satisfy the convexity on every small domain, then you satisfy it everywhere. If you look at it from this point of view, it's not so obvious. But from this point of view, it is obvious because it is local. And the final remark is that the first definition is very good when you have limits to consider. It is very stable. Imagine that you have a sequence of functions, phi k, converging to some sequence, to some limit, phi infinity. Okay? If each of the phi k is convex, how do you prove that the limit is convex? Well, you can try with this, and you see that it is easy as long as the second derivative converges. But this is a very strong requirement, convergence in with two derivatives, like C2 topology. But here, it's so easy. You just need to know that the function converges pointwise. For each x, it should be phi k of x goes to phi of x. Not even uniform convergence. So this is much more flexible for stability. So we see that each definition has its advantages. And one of the reasons of the success of convexity is the fact that you have both at the same time. And part of our, for instance, typically if you want to prove convexity of some limit, you will use this to prove that there is a convexity for a sequence, and then use this to pass to the limit. Now let us do it for the simple Euclidean geometry, which is often our first contact with mathematics. Synthetic is known since the thousands of years. This is the point of view of the Greeks, in which you have properties of circles, triangles, etc. Euclid axioms, and so forth. But we learned at school, but it was actually a discovery of the 17th century, that you can also do it with equations in an equivalent way, with equations like this or like this. And this is equivalent, but it's analytic point of view. It's more systematic. It is, in a way, easier to check, but somehow this is more satisfactory. This insists more on the properties, and somehow one has the impression that this is more robust. It depends only on a few axioms. So what about non-Euclidean geometry? Okay. In non-Euclidean geometry, the most important concept is the one of curvature. And the curvature usually, by default, is the sectional curvature. And if you are in dimension 2, this is the Gauss curvature. How do you define the sectional curvature? Okay, here is one way. If you have a manifold X, and you take a point X in your manifold, and you take a plane in the tangent space of M. Okay, so this will be a plane, and now you take U and V, orthogonal vectors of unit norm in the plane. Okay, so this is the situation. And you will see how they separate from each other, the geodesics, which are starting from X with these unit geodesics. So this is X TU, this is X TV, and you ask about the distance between them. Curvature is about the separation of geodesics. If there is no curvature, then the distance would be equal to square root of 2 times t, Pythagoras. Because there is curvature, there is a correction. The first ingredient in the correction is 1 minus kappa over 12 t squared as a factor. And then there are higher order terms when t is approximately 0. Notice, positive curvature means the separation is less. Negative curvature means the separation is more. Okay? So, distance between them has this correction, and this guy here is called the curvature. From this expression, it is obvious that curvature is invariant under isometries, but as we know, there is also another way to define curvature based on the determinant of the Jacobian map, and then it's a difficult theorem to prove that it is invariant under isometries. This is a famous theorem of Gauss. Whichever way you define curvature, if you use this formula or Jacobian determinant, it will be an analytic formulation. And now you see it's about second derivatives of distances between geodesics. Now, is there a synthetic definition of sectional curvature? The answer is yes, but one does not try to define the sectional curvature. One only tries to define the bound. Positive curvature or negative curvature. So when I say positive curvature, it will mean curvature bounded below by something, or curvature bounded above by something. And instead of trying to define the curvature, you try to define what is a space which satisfies curvature bounded above by 2, for instance. Why bound? One reason is that curvatures often come into play by bounds. Another reason is that there are comparison principles with curvatures, a bit like with convexity. So when we want to say that curvature is negative, we want to compare this to the Euclidean plane. So let us give one example. So this, first let's say that these spaces are called cat plus k0. These spaces are cat minus k0. CAT stands for Cartan, Alexandrov, Toponogov, who developed this kind of synthetic theory at various times. So for instance, let us define CAT0, and there is a definition. So XD, a geodesic metric space. Let us say compact, even though we can relax this. Is said to be CAT plus 0 if for any ABC triangle in X, if A0, B0, C0 is an isometric triangle in the plane, Euclidean space of dimension 2, then the distance between A and the midpoint of BC is bounded below by the distance between A0 and the midpoint of B0, C0. So it means this. Here is my triangle, ABC. Here is the plane. Here is the isometric triangle. So this is equal to this, etc. And I compare the medians, this here, and the distance should be at least this. Okay? So this is a definition. A space.
Sir, quickly, it's possible to tell us what is geodesic metric space?
Yes. Definition. If X D is a metric space, then define and gamma is a path from 0L to X. Let L of gamma be the length of the path, which you can define in two possible ways, which are equivalent. So one way being, okay, let's assume that it is a Lipschitz map here. First way is to say that it will be the supremum of the sum of distance from gamma of ti, gamma ti plus 1, I going from 0 to n minus 1, supremum over n, and a supremum over all possible partitions, 0, t1, etc., 0, t1, etc., tn with 0 equal t0, tn equals 1. It means that we are computing the length like this by subdividing into many little things, and this is distance, 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 distance. This is a very intuitive notion of distance. It's exactly the one that we use at school to measure the length of a path. So it's a very intuitive notion of length. And when you take this, and the supremum exists, and it's also the same as to write this as the integral from 0 to L of the metric derivative gamma point t dt, which is the integral of 0 to L of the lim sup as epsilon goes to 0 of distance from gamma of t to gamma of t plus epsilon divided by epsilon. And you integrate this with respect to dt. Okay. So this is the other notion. These two notions exist in compact spaces, and more generally in spaces which, in some more generally in locally compact complete spaces. Anyway. So, and the second definition is a geodesic is a curve gamma going from, let's say 0, 1, you can always reduce to this case to x, such that the distance between gamma of 0 and gamma of 1 is equal to the length of gamma. And in this case, it is the minimal, it is minimizing the length. And without loss of generality, one may assume that the derivative is equal to the length of gamma at all times t, up to reparametrization. Okay? And the final definition is that xb is the geodesic if for any x and any y, there is a geodesic gamma such that gamma of 0 is equal to x, gamma of 1 equal to y. So it means that any 2 points can be joined by a geodesic path. Geodesic spaces are a quite important subset of metric spaces, and let us say that the most general notion of geometry is with metric spaces. Of course, it is debatable what you call geometry, but let me stick to metric spaces as the most general possible. And then a sub-part of this is geodesic metric spaces. An example of a geodesic space could be a tree, you know. This is not a manifold because you have things, but still it is a geodesic space. If I want to go from here to here, well, there is at least one geodesic joining them. And an example of a metric space which is not geodesic is any discrete space, because if my space is discrete, obviously there is no way I can join two different points by a geodesic. So geodesic spaces are not the only thing, but it's an important category.
For the path connected one also you have?
For the
Path connected one also you have a non-geodesic space?
yes, yes. If you're, well, you can always, you need path connected, starting from the distance which is non-geodesic, you may always define one which is geodesic. But look at this example. Take the metric space, this is a square, okay? It's a geodesic space. Now remove one point and look at these two, from this to here. You cannot, there is no geodesic, would have to go from here. You see? Okay. So,
yeah, there are complete spaces without any rectifiable paths.
And there are
snowflake spaces.
also snowflakes, spaces, things like this,
Complete.
that will give you some headache.
So what is the example?
They have no rectifiable paths. Square root of the Euclidean.
So this one was not complete.
This one is not complete. That is complete.
Yes, but let's give another one which is complete and not snowflake and still not geodesic space. Let's take this part of the plane with the usual distance in R2. then of course, if I want to have the geodesic from here to here, I would have to go from there. On the other hand, from this one, which is equipped with a non-geodesic distance, you can transform this into the geodesic distance by taking the supremum of the length of the path, which go from here to here. And it's the notion of intrinsic distance rather than extrinsic. So whenever you take a sub-geometry, somehow, if there is some rectifiability, you can take the associated inner distance. And when it is not rectifiable, then you cannot even do this. So the great book for this is the book by Burago Ivanov, which has many misprints, but is a beautiful book, and that develops the whole theory of geometry in metric spaces, insisting on the notion of non-smooth curvature. So let us give some examples. So the examples of cat spaces. So a tree is often associated with negative curvature, and indeed it is a cat minus space. But in a way, there are parts in which the curvature is minus infinity, these branching points. On the other hand, there are some spaces which are cat plus, are never too bad. An example, the most simple example maybe, is a cove. So, example, let's take this. You see this cone here. Of course, it's not a manifold because there is a singular point here at the apex, but it is still a cat plus space. And if you would look at the curvature, in fact, it would be zero everywhere except here where it will be a Dirac mass. And in this case, because it's simple, you can even work out which weight you would give to the Dirac mass, because the famous Gauss-Bonnet formula relates the shape of triangles to the integral of the curvature inside. So if we draw a triangle inside, if the triangle does not enclose the apex, it will be a Euclidean triangle, and if it does enclose the apex, it will be a non-Euclidean triangle. The sum of the angles will be bigger than pi, and it will still satisfy always this relation. And then you can imagine spaces in which the set of singularities, it can be many points, it can even be dense. On the other hand, there are results saying that it will be very small in the sense of measure and things like this. And these cat plus spaces, there is a whole theory about them. There is a theory for cat plus, a theory for cat minus. First, this I define it for cat plus 0 by comparing to the plane. But if I want to define cat plus 1, I compare it to the sphere of radius 1 rather than to the plane. The idea is to do some comparison. Cat plus spaces have been studied by a number of people, and there is a well-developed Russian school of these spaces, also a well-developed Japanese school, and also, let's say, there is a less developed but present German school. And these spaces have some properties, like for instance, they can never be too bad. They are much better than cat minus spaces. For instance, a cat plus space of finite dimension, say in the sense of Hausdorff dimension, on it you can always find some kind of charts, some kind of coordinates defined almost everywhere. You have some tangent planes defined almost everywhere, and things like this. There is even a parallel transport defined almost everywhere in some sense. It is reminiscent of the fact that if you have a convex function, just knowing that it is convex, you know that it has almost everywhere a differential, and even almost everywhere two derivatives. So there is some automatic regularity almost everywhere which comes with this structure. You can define a Laplace operator on a cat plus space, etc. And it's technical, and there is a little industry about this. Cat plus spaces appear, for instance, in Perelman's proof of the Poincaré conjecture. What to say more? Well, there is a developed body of work about all this. And one other important thing about the whole is the so-called Gromov compactness theorem. I will come to it later and present it in a more general setting. Okay, this is sectional curvature. Now, as we know, there are several curvatures, and for people doing dynamical systems, sectional curvature for sure is the most popular. But for people who do probability theory, clearly Ricci curvature is the most popular. So whenever you are handling distances and measures, the Ricci curvature is the most important. So what is Ricci curvature? Let us give an analytic definition, and simple will be, still I have x here in my manifold, and then E, a unit vector, E in Txm, norm of E equals 1, and I want to define Ricci in the direction E. So Ricci curvature, Ricci actually is a tensor, and Ricci in the direction E will be the sum of the sectional curvature in the plane generated by E and EI for I going from 2 to n. N is the dimension of the manifold here, and E, E2, etc., En will be an orthonormal basis of Txn. So I adapt sectional curvatures in all possible planes containing the unit vector E. This defines the Ricci curvature on the unit sphere, and it turns out that it can be extended into a quadratic form, which is not obvious from this definition, but becomes obvious if you can identify it with a certain contraction of the Riemann tensor of R, something like that. Okay, up to some mistake in the indices. So this Ricci curvature, what does it mean? Several ways to look at it, but I will just give a meaning of Ricci non-negative, one possible way to see it. This is X, and imagine that this is a set, or even, let's say, this is a set, a full set A in M. Okay? And you are interested in how it is seen viewed from X. So, viewed from X, here is this geodesic, that geodesic, etc. And when I see things from X, what I see is the way it arrives, you know, here. And it's like when the light has a deviation and you are mistaken, then you will believe that actually what you see is something like this. You know? This is what you see. This is the real object, and this is what you see because the light is distorted. Okay. So let's call this A prime. Okay. And Ricci non-negative is equivalent to say that the volume of A prime is always bigger than the volume of A. Meaning you always see objects larger and as they are in reality. That is the meaning of non-negative Ricci curvature. There is a
For M you have excluded geodesics?
Excluded what?
No, for M you have started with M and you have
Yes,
excluded
X is also in M.
for manifold is also.
Yes.
Okay.
Yes. So there is a certain picture which is always associated with Ricci non-negative. It is this, that if you look at the geodesics between two sets, they always do something like this. Okay. It's a picture that you always keep in mind in this context. First diverge and then converge. And you know, saying that it is in Ricci sense is that it is in the mean. Okay. So let me give you one of the most remarkable inequalities in this context, which will also capture very well this meaning of Ricci curvature. And you know, I use some midpoints for the cat, for the cat notion. I should have said something else that everything I said about the advantages and drawbacks of the synthetic analytic point of view here are also true there. For instance, it's very difficult to check in practice that the geometry is cut. But computing this, okay, there are some formulas, it's systematic. On the other hand, there are some non-smooth geometries here. And most important, when you want to pass to the limit, if you want to pass to the limit in this, it requires a strong notion of convergence of the geometries, while here, it requires a very weak notion of convergence, and that notion is the Gromov-Hausdorff convergence, which basically says that the distances should converge. The natural topology on the set of metric spaces, of geodesic spaces, this Gromov-Hausdorff. So here is a theorem. The curved Brun-Minkowski inequality it summarizes very well the meaning of Ricci curvature. It is a bit shocking to know that this inequality was discovered only around 2000, so 2001. What is it? So if your manifold M has dimension n and has a Ricci non-negative, then for any sets, let's say compact sets, A and B, okay, in M, the volume of the set of midpoints of A and B, you know, whenever you have a geodesic going from A to B, you look at the half point of the geodesic gamma of 1/2. This is a midpoint, one midpoint, and maybe there are many midpoints between 2 points, but there are a set of all midpoints between A and B. Is when you put it to the power 1/n, it's bounded below by half the volume of A to the power 1/n plus the volume of B to the power 1/n. In other words, midpoints are large sets. If I have one set and another set, and I look at the set of all intermediate points, it is rather large. It cannot be too small because of this inequality. So this captures very well this. Now, here is the basic question. Okay, now let's say some more things about Ricci curvature. So first, it involves distance and volume. So often you are interested in geometry in which the volume is given by the distance. You know, the Riemannian volume is the Hausdorff measure associated with the distance. But sometimes you want to introduce a volume which is not related to the distance. And every time you have a probability measure which is given, it can be useful. And so it's natural to change the definition if the volume is imposed. What does it mean, imposing? Well, maybe your manifold is R with the usual distance, but you want to consider the Gaussian measure as a volume on it. And you want to think of it as a geometric space with a measure. So there is a whole way to change all this, and a dictionary which works very well and which has been developed for many years by probabilists working in geometry. And they know that if you have a Riemannian manifold Mg, but you work with a volume measure exponential minus v times the Riemannian volume of G, then there is a way to define the Ricci associated with V. I will give the formulas here. Ricci V is the classical Ricci plus Hessian of V. This is my notation for Hessian. Okay, and in this way, we can think of this as positively curved, even though the base space is flat. And this is a way to make the connection with the fact, in probability measure sense, we like to think of this as a limit of spheres of very high dimension, and there is a way to pass continuously from the curved high-dimensional sphere to this space, which is curved in some sense.
Can this curvature be thought of a Ricci of some other metric on the sense space? Is it possible otherwise? Or?
Not always
Not
possible.
always possible.
Not always. In general, not possible. Sometimes yes.
Sometimes.
Yes. And what to say more? Yes. So Ricci appears in spectral bounds, isoperimetric inequalities. It appears in volume comparison. It appears in Poincaré inequalities, etc. And Sobolev inequalities, etc. And there are names, famous inequalities associated with this. Also diameter control. This is called Bonnet-Myers. If you have a lower bound on the Ricci, positive lower bound on the Ricci, upper bound on the dimension, then there is a bound diameter. This is called the Bishop-Gromov inequality. This is called the Levy-Gromov inequality. This would be the Lichner-Rovitz inequality. There are families of inequalities like this. And it's always, you want the lower bound on the Ricci, K, the lower bound, and an upper bound on the dimension, say capital N. And it comes so often that there is a classical word for a notation for the combination of these two, is CD of Kn, mean curvature dimension bound Kn. Ricci bounded below by K, dimension bounded above by N. Okay. Now, very good. There is a remarkable theorem. It's not difficult to prove, but it's remarkable. The compactness theorem of Gromov. If you look at all the set of all manifolds, of all, let's say like this, mg with some measure nu, such that there is a curvature bound, so Ricci bounded below by k, dimension bounded above by n, and the diameter is bounded above by d. So the set of all this is precompact in the measured Gromov-Hausdorff topology. So measured Gromov-Hausdorff means basically that distances converge and volumes converge. So it's the extension to the metric measure space setting to the usual Gromov-Hausdorff. So if this thing is precompact, it means when you consider sequences of geometries cannot go too bad. And the bound on the Ricci curvature ensures this. This theorem would be false with an upper bound on the Ricci. It's really lower bound on the Ricci. Lower bound on the Ricci prevents some spikes to occur and get out of control. Lower bound on the Ricci curvature are also used, by the way, to define the heat equation. If you want, like, can I define a heat equation on my manifold if it is infinite? The answer is yes, if there is a lower bound on the Ricci curvature, or at least if the Ricci curvature doesn't go to minus infinity too fast. So, question, can we describe in some sense the closure of this precompact set? Can we define Gromov, can we define the Ricci curvature bound on metric spaces? Can we give a synthetic criterion for Ricci curvature? And this is the question, this was the problem, and you can find this problem in the papers by Gromov, for instance, or in the works of people who are interested in these kind of limits, Chigger, Kolding, etc. And so this is the problem that for which we gave a solution, which let's say started around 2004, and the theory can now be said to be satisfactory, and this is what I will explain.
Question.
Yes.
In this Ricci V, do you need V to be a quadratic or something like that?
Yeah, it could be quadratic. V could be V is a potential function, a function defined in a manifold. Yes, it could be quadratic. This would be like a Gaussian space, but it could be other things as well. Yes. Yes. Yes.
The question about the compactness theorem, where does the measure nu come in the hypothesis?
In the measure, this is here measure
So
measure
this-
composed of.
It's not related to the CDK in your statement.
Oh yeah, yeah, yes, yes,
The
yes.
nu comes in the CDK.
Yes, absolutely. Hold on. Oh yes, here, yes. Here you don't care. You're right. No, it would be. It is included in the CD. I mean, here by this
With the effective Ricci.
with the effective Ricci. Absolutely. So, other question?
Okay, so that means effective Ricci bigger than kg. That's the hypothesis.
Absolutely. Effective Ricci, this bigger than k times g. This is the C would be the. This would be, oh gosh. Here I cheated you a little bit. This would be CDK infinity. I have to be a little bit more precise if n is not finite. CDKN is exactly this. Ricci plus Hessian V minus grad V times grad V divided by n minus n bigger than kg. For some reasons you have to put these corrections if the n is not infinite.
So does this work? I mean, this makes sense if nu is absolutely continuous.
Only if it is absolutely continuous.
Otherwise, that's
There is a speculation and some partial results that when you have a manifold and a certain measure that makes it Ricci bounded from below, then any other measure will be absolutely continuous respect. There is this conjecture that there is only one equivalence class in terms of absolute continuity. Yes. Other question? Okay. So let us. Here is the definition. So, okay. So let's say that there is the theory of synthetic Ricci. Along the way that I will say there are some precursors which were a paper of Otto and myself, in which it was all mixed, let's say. The ingredients appeared, it was in Journal of Functional Analysis, maybe 99 or 2000. There was a paper by von Renesse and Sturm and von Renesse, a couple of years later, maybe in CPAM. Then the papers in which things were really developed, there was the paper of Lot and myself. This was in Annals of Math. And there was a paper of Sturm which appeared in two parts in Acta Mathematica. And in these two, this is Lot, in these two was developed the idea that let's give a new definition of Ricci curvature bound, so synthetic definition, and start everything from there. People now call these sometimes LSV spaces for Lot, Sturm, Villani, and I will give the definition first in the simplest case. And the idea is to use only measure spreading along geodesics to define the Ricci curvature bounds. Okay. So, what is a geodesic? Well, start point, final point, and I look at the shortest path between them. If there is just one geodesic, then how to define a spreading? I would have to make a variation of this point and look at the Jacobian determinant. When the geodesic varies, this is the Jacobian determinant of the exponential map. And actually the fundamental calculation for the properties of Ricci. But how to define the Jacobian determinant in a non-smooth space is, well, there are tricks and so on, but it's delicate. Another approach is to spread from the beginning. Instead of saying I want to go from this point to that point, say I want to go from a certain measure to another measure, and look at the optimal path, which will be now in the space of measure, so that I will interpolate between the initial probability measure to the final probability measure